we wanted to do one thing, if you remember. We wanted to compare the results, right? Euler method. Let me just write something like harmonic oscillator Euler equals to, what is it? X values, right? So let's run it again. These were harmonic oscillator result using Euler method. And then the Verlet integration gave us harmonic oscillator Verlet X values. Do you see it? Just simply understands what I want to do. Okay. Let's see whether it's going to understand what I want to do next. Okay. Oh, no. I want to do Euler minus. I want to do this, right? The difference. Are you with me? Yes. Okay. You have to first what?
Subtract them, because you're subtracting list from list.
What do you mean by that? It's good that we have you. So explain.
Both of these are lists.
Yeah?
You want to subtract the first element to the first, second to the second, third to the third.
Yeah.
So it's not directly subtracting it. You're subtracting list from list.
So should I go with MPy array or something like that? Will it work? Okay, good. Do you see that it's growing quadratically? Yes? We can also do absolute value of it. It's growing quadratically. Seems to be. Okay. Let's think about two balls and a spring. So when you have two balls and a spring, what do you do? Let's say this is M1. So far there was always one object, right? Now you have two objects. And I'm going to write things in terms of the displacement from the equilibrium points. So they might have equilibrium distance that is L apart. So, for example, what is the if this is spring constant K, what is the formula for M1 d squared x1 over dt squared?
Minus K times x2 minus x1.
The way that I do this is I always remember that I will always remember Hooke's law. So whatever I have here, x1, I should have negative sign in front of it, and otherwise it should be a difference. So what do I mean? K times x2 minus x1. Does it make sense? Let's write it down for the second one. M2 d squared x2 over dt squared is?
Opposites.
Exactly. K times x1 minus x2. Does it make sense to everyone? Yes? Now the rest is same story. The rest is just Verlet integration. Okay? For example, the first part of your homework is to do it for 3 objects. So we will do it here for 2 objects. You will do it at home for 3 objects. Okay, so mass, the spring constant, mass of the first ball, the rest length of the spring, time, initial conditions, t values, x1 values, x2 values. Then what do we have? The acceleration. So dx is the distance between them. So a1 is x2 minus x1, k times x2 minus x1 divided by m1. Does it make sense? Yes? And the other one is negative of that. This is actually Newton's third law, right? Action equals to reaction. But it's acting on the opposite objects. All right, then what do you have? You have update for the positions, then you find the next acceleration, then you update the velocities according to Verlet algorithm. That's it. And you can draw this and you are going to get this kind of. So you see here you have actually the initial velocity is just one of them has this velocity. So center of mass of the whole system has a velocity. That's why they are going like this. Okay? Oops. No. Very good. Let's animate them, although I'm not doing a good job with this. But do you see?
Yeah.
It's very nice. Now take a deep breath, because we are going to talk about time evolution operator.
Center of mass is half the velocity of the first one, right? Center of mass.
Center of mass velocity is probably, so the velocity is probably m2 times v2 over m1 plus m2, right?
Then
Because
a third of the speed.
a third of the speed, yes, very good. Because momentum should be conserved. And you know why momentum should be conserved? Who can tell me?
Newton's theorem.
Noether's theorem, very good. That was actually a joke, but by answering the right answer, very impressive. Very good. So let's go ahead and make our lives harder, okay, by just talking about this stuff. So you see, this is the second order differential equation, and it's a system of second order differential equations, but we can go to the first order. It is possible. How do we do that? We use these other variables, right? So let me go back to here. Oops. So if I write dx1 over dt equals v1 and dx2 over dt equals v2, then I write dv1 over dt equals whatever I got for the acceleration, which is k over m1 x2 minus x1. And finally, dv2 over dt equals k over m2 x1 minus x2. So far, did you follow this? So you can actually write a vector r, which is x1, x2, v1, v2. And you can actually turn it into a differential equation with a matrix. Okay? So you have a vector that has the variables. Are you following? Yes? So on the left side, you have d of x1, x2, v1, v2 divided by dt. Then you have a matrix. Then you have the same vector over here, x1, x2, v1, v2. Who can tell me how to write the elements of the first row based on this equation? So apparently dx1 over dt is v1. 0, 0, 1, 0. Very good. Why? Because this row will be multiplied by this column and it will pick up only v1. Does it make sense? Very good. What is the next one? 0, 0, 0, 1. Very good. Very good. And the next one? Minus k over m1. Very good. And plus k over m1. Do you agree? 0, 0. And then the opposite. And also with m2, right? K over m2 minus k over m2. 0, 0. So what we have turned it is we have turned it into this kind of equation. Matrix A times R. Okay? Hopefully, without doing any mathematical sin, we can write it like this. Okay? And then integrate it. Then you are going to get ln of this r, right? Here. And then you are going to get a times t here. Are you following? Yes? Then r is exponential to the power of a matrix times time times r0. Have you seen a matrix at the top of exponential before?
Yes, in quantum mechanics.
In quantum mechanics. Why did you get quantum mechanics? You are a graduate student.
No, undergrad.
And? Which year?
Third year.
Third year, okay. You are taking it now?
I took it last semester.
Okay. Who else knows what it means to have a matrix? You also know, but some of you don't know, right? Some of you are seeing it for the first time. So let me explain it. And it's also present in the prerequisite videos, okay? I don't know how fast I have talked about that there. First of all, do you know this one? Was it 6? Yes. You do know this one? Yes? Now, when it's a matrix, ask me. Tell me. Taylor expansion. Yes, very good. Very good. Now, you just replace that x with a matrix. Okay? So, e to the matrix is going to be identity matrix plus that matrix itself plus the matrix squared over 2 plus matrix cubed over 6, etc. It goes on forever. Now, how do you cube a matrix? You just multiply the matrix by itself 3 times. Okay? Is everything clear here? Yes? So it's yet another way of solving the same problem that we have just solved with Verlet algorithm. We have just solved Verlet algorithm. Now we are solving it using time evolution operator. So let's see what we have. We have initial conditions, and then we have this matrix, right? The matrix is just the one that we wrote. Yes? And then there is this time evolution operator, which is, do you see, it's not exponential a times delta t, it's exp m. You know, exp matrix is just taking element-wise exponential of the matrix. Okay? That's a different thing. This exp m is a package from SciPy linear algebra package. From SciPy linear algebra, import exp_m. So it's a special thing. And this is going to calculate that e to the a delta t that we had over here. Okay? So what are we doing? We are doing the following. We are saying that r t plus delta t is equal to e to the a matrix times delta t times rt. That's how we are going this time. But this one has its own peculiarity in a sense that we are actually taking into account all higher orders in principle. We are taking t cubed, t4, t5, t6, everything is there. Okay? So, your initial state vector is the initial values, and then it's just r is equal to this time propagation matrix, time evolution operator, times the current value. Yes? Okay? Good? Amna? Yes? So, let me run it. Do you see? You get the same result. Just like here. I started with the same initial conditions and it gives me the same results. So your homework will be to do these two things for 3-body system. Very easy, right? Yes?
3-body extraction or like one in bidirectional extraction?
What do you mean?
Like 3 poles, how they will be?
In one dimension. No, in one dimension. Speaking of 2 dimensions, are you familiar with double pendulum? Yes, mechanical engineers. So let's just go to its Wikipedia page. So we are going to do a simpler version of it. We just have a rod that is massless, and there's a mass here, and a rod that is massless, and a mass here. Okay, so if you want to get the equations for it, it's not an easy task. Let me show you this other thing. So they are trying to, not trying, they are actually doing it. They are figuring out the equations of motion from all these kinds of investigation of forces, accelerations, and whatnot. Okay? It's not an easy task. You can always get yourself confused. And in the end, they get this equation. Do you see it? So the acceleration of the first angle depends on the first angle, the second angle, the velocity of the first angle, and the velocity of the second angle. Okay? And then it's not at all an easy equation. Okay? You can arrive at this equation either by doing very careful analysis of forces or very careless analysis of Lagrangian, right? Have you done Lagrangian stuff? Mechanical engineers have done, and for others you shouldn't care. Anyways, but you should care because it's beautiful. You see, you just write kinetic minus potential energy, and you plug it in the Euler-Lagrange equation, which looks like this. Like this. It looks complicated, but it is complicated, yes. And if you do the Euler-Lagrange equations, you get this. Seems to be simpler than what we just saw. Let me get myself out of the way. Maybe the equation that we saw there this equation seems to be simpler than this equation. But the reason it looks simpler is because here everything is together. Like theta 2 double dot is here, theta 1 double dot is here. So you need to do an extra step of separating them. And while you are doing that extra step, it gets much more complicated. All right? Anyways, this has nothing to do with your homework, so just chill and just watch it. Watch what happens. All right. Same story, some initial conditions and whatnot. But here, let me do the following. So these are for plotting. We are figuring out x, y, and coordinates for the two balls. And then, where am I calculating? I'm calculating here. Do you see this long equation? Yes? I didn't write it. I write on the title double pendulum, and I just clicked tab, and the computer understood that I want this huge equation. Very nice. Now, this is numerator, this is denominator, and this is acceleration 1. Numerator, denominator, acceleration 2. Now, this shouldn't be there. No, this is correct. This is what you do, right? X equals to x plus v times delta t plus a times delta t squared, etc. Right? But this wasn't there. Predict next angular velocities. This wasn't there before because so far, where are you? So far we have looked at, that person is gone? The person who said that what we have looked at is a special case where a is minus k over m times x, where a depends only on x. And she told me that we have seen cases where a depends on velocity as well and things like that. And I told her that you are going to see that case too. But my prophecy was wrong. So she couldn't see it. But in any case, I will turn it off for now because we didn't see this yet. What we saw is that you get the next accelerations and you update the velocities. Now, we will see that there will be again a problem with energy. I'm calculating energy here, kinetic energy, potential energy, then I'm printing kinetic plus potential energy, okay? So let's run it. Okay. Okay. Let me do the following. Since I've changed the code, let's say it is not changed. Do you understand it? Yes? I haven't changed it, so this is our double pendulum. And this is the energy. Do you see? It swings back and forth. Not the pendulum. Pendulum also swings back and forth. The energy also swings back and forth. And it is not conserved, right? But if I include that, and I don't know the name for it, I don't know what this is called. Whether it's still called Verlet. You are here. Yes, sorry. You are here. My prophecy was right. Okay, sorry. Are you happy?
Yeah.
You are also happy? Good. Now, we have predicted the next angular velocities. And I don't know what it is called. Does anyone know what it is called? Do you understand what's going on? You understand what's going on, right? Yes? What's going on is the following. Before, acceleration was dependent only on the position. So when we calculated a next, we were using only the positions that we have found for future. But this time, we are also using predictions for next time velocities, because our acceleration depends also on velocity. So I'm plugging my prediction for the next velocity as well when I'm calculating the next acceleration. Yeah, okay. And when you run it, as you can see, it does swing back and forth, but it swings much less than before. Okay? Everyone is happy? Yes? Okay, very good. I was planning to stop here, but since I didn't, I will go further. Okay. So let's see what we have here. Okay, I'm going to introduce you to something that sounds intimidating. It's called dynamical matrix formalism. Okay, have you heard about this? No? So I'm going to go over a particular example, and this will help you. This will even help you with the homework, so it's good. Because this particular example has 3 bodies. Consider these 3 bodies, and you might be thinking that this is an arbitrary thing. Why we are bothered with springs and masses? And as I said before, many things can be thought in terms of springs and masses. I will call this K12, this one K23, and I'm going to also connect the first one to the third one, so that you get over that thought that things can only be connected when they are neighbors. They may be connected also when they are next neighbors, right? Okay, so what is the equation for the first one?
K times x2 minus x1.
K12 times x2 minus x1. Anything else?
And 1 3 term. K13 x3 minus x1.
Everyone is happy? Did you understand this? Yes? So then the rest is also similar. x2 is dt squared K12 x1 minus x2 K23 x3 minus x2. You see, I'm not even thinking whether I should write x2 minus x1 or x1 minus x2. I always think that x2 should have negative. Okay? So that really helps you. M3 is d squared x3 over dt squared equals K13 x1 minus x3 K23. Did I make an error? No. x2 minus x3. Hopefully these equations are correct. Now, what I want to do is to go from here to something that looks like this. An eigenvalue equation. I want to start from this set of equations and arrive at an eigenvalue equation. Have you heard of eigenvalue equation? Yes, you have. Okay, good. where this matrix is going to be symmetric dynamical matrix. Okay, and this is going to be frequency of oscillation. That's where I'm trying to go. Where do I start? I start by saying that x1 of t can be considered to be e to the I omega t times u1. Okay? Why e to the I omega t? Because if you have watched the preliminaries, e to the I omega t is a zipped version of sines and cosines already. It's easier to work with it. Although it always has that impression that everything is going to turn up as complex numbers, but they are not. Everything will turn into real numbers eventually. Okay? Very good. So what do we achieve by this? We achieve the following. D squared x1 of t over dt squared is minus omega squared e to the I omega t times u1. u1 is a number. It doesn't depend on time. Every time dependence is being put in e to the I omega t. Hopefully you are following. What do we do next? Well, I want omega squared to be on the right, so let me put these terms on the right and the other terms on the left. So let me just write it down. Let me take this, copy it, paste it here, and actually let me copy all of them so that you are not bored. Copy all of them, copy, paste them here. But this time, the masses, you had this m1 d squared x1 over dt squared, right? That becomes minus omega squared u1, where this one also becomes u. So these all become u, and the exponential terms cancel out. Okay, you tell me if you understood this or not. So we went from algebraic equation, from differential equation, we proposed the solution, and we arrived at a set of algebraic equations. So far, so good? Yes? Any objections?
This is for initial velocities are all zero, right?
No. We haven't talked about initial velocities yet. We are solving it as a general case. Okay? We are solving the homogeneous part. Let's call it like that. And we are going to get eigenvalues and eigenvectors. And we are going to figure out their behavior. Then the initial conditions will be defined in terms of those eigenvectors. So the initial condition will be separated into eigenvectors. And we are going to, we are actually not going to do that part. We are just interested in the general solution of this. Although, are you with me? You seem super bored. Like too much information or something happened to you. Okay. So let me write it down as a matrix. It seems like we have already achieved our goal, but we haven't. We have, by the way, that will be a major problem, so let me write these. So we have u1, u2, u3, then we have omega squared, m1 u1, m2 u2, m3 u3, right? And I have multiplied it with negative sign. So we get k12 plus k13 minus k12 minus k13 minus k12 k12 plus k23. It's so obvious that you are bored.
Zero. Should it be minus k13?
Excellent. Old habits. Old habits of not connecting the first one to the third one. Have we achieved our goal?
No, this isn't an eigenvalue equation.
What?
This isn't an eigenvalue equation, so no.
This isn't an eigenvalue equation, right? Why it is not?
Because the right-hand side vector is not linear dependent with the input u vector. But
Do you-
it's a generalized eigenvalue equation.
It's a generalized eigenvalue equation. Very nice. So, very, very nice. Do you see this vector should be the same as that vector, right? But at least we have a symmetric matrix. That's something, right? Must be something. Good. So that symmetric matrix actually has a name. Let me put it somewhere here so that it will remind us where we are trying to go. This matrix is called the force constant matrix. Okay, so what do we have? And let's try going to some places where the vectors will be the same. So I have force constant matrix times U matrix equals omega squared times the mass matrix times U matrix. What is this mass matrix? Mass matrix is just M1, M2, M3, 0, 0, 0, 0, 0, 0, 0. Do you see that when you multiply this with U, you get this matrix? Does everyone see that? Yes? This is one of the longest derivations. So now we will do some matrix algebra so that we get actually something in this form. Here's what we do. Can I write M let me write something like this, square root M matrix, or square root of the M matrix. I don't know which one I prefer. Okay, let me go with this one. Can I do this?
Yes.
And what is square root M matrix?
In this case, 0.5 square roots.
In this case, it's just this one, right? Because it's diagonal. Everyone is still with me? Something really nice will happen soon. Just trust me. Can I insert here square root M inverse times square root M? Yes, I can. So F times square root M inverse square root M matrix equals the squared M square root M. Okay. Now the problem is, okay, sorry, there's U here, right? We are almost there because now we have a vector that looks like each other, right? but I still have this matrix here, and this matrix over here is not symmetric anymore. Because, let me show you why. A, B, C, B, D, E, C, E, F. This is a symmetric matrix, right? Let's multiply it with 1, 2, 3 over here. What will you get? A, B, C. No. What do I get? A, 2B, yes. A, 2B, 2C. A B, what? 3C, yes. 2D, 3E. C, 2E, 3F. So it's no longer symmetric, right? But if you also multiply this one from this side, what will happen? A, 2B, 3C, 2B, 4D, 6E, 3C, 4, no, should be 6, 6E, 9F. Do you see? It's symmetric again. So if you multiply both sides of a symmetric matrix with a diagonal matrix, with the same diagonal matrix, then it's still symmetric. So what we are going to do is multiply both sides with square root m inverse from left here and from left here. Okay? So we have arrived at our solution, and this one is going to be 1. We have arrived at the formula that looks like this. Dynamical matrix, I'm giving errors too. U equals omega squared U. Okay? So this is the vector, the eigenvector. These are going to be eigenvalues, and this dynamical matrix is square root m minus 1 times the force constant, square root m minus 1. Okay, so let's write the dynamical matrix in its full glory. So let's copy this one and paste it here. So we have basically this same matrix, but we are going to have divided by m1 divided by square root m1 m2 divided by square root m1 m3 divided by square root m1 m2. Do you see it? It's still symmetric. Does everyone see that? Why do we like symmetric matrices? Real eigenvalues and
orthogonal eigenvectors.
Orthogonal eigenvectors. Very good. Square root m1 u1, square root m2 u2, square root m3 u3 equals omega squared square root m1 u1, square root m2 u2, square root m3 u3. Very, very good. Everyone is happy? Huh? Now let's go back to coding. You didn't like coding, you hated this one, right? So I'm going to write down dynamical matrix for a system that is composed of just two, so like something like this, M, and there's K, and there's M again. So its dynamical matrix is basically K over M minus K over M minus K over M, K over M, like that, right? Now, we are going to create eigenvalues and eigenvectors, and this is omega squared, remember that, okay? Since I have taken M to be 1, I'm not bothering with division by square root M here. But I just wrote this code, so I will improve it. Let's look at the first eigenvalue. Remember how we count? 0, 1, 2, 3. So the first eigenvalue is n equals to 0. Let me run this. Let's run again. Okay. So the first eigenvalue looks like this. We took 2 atoms, and eigenvalue is like this, okay? And it has some omega. We can actually look at the variables, and we can look what is omega. Where is omega squared? Even the computer is bored. So the first eigenvalue is omega squared equals to 2. The second eigenvalue is 0. Do you have any interpretation for that? Doing nothing is an eigenvalue DC. Very good, very good. Brilliant. So, I will talk more about this. You are too bored, too tired for today. But the second one is just doesn't have, for the second one, omega is 0, and the eigenvectors for that one, let's look also eigenvectors. So eigenvectors for them are pointing in the same direction. It's basically corresponding to the following. If I take 2 balls that are connected with a spring, and if I move them together, then there will be no restoring force. Okay? If I move them together, there will be no restoring force. That's the second eigenvalue that has omega equals to 0. If I move them like this, then there will be a restoring force. And you can define any movement by combination of moving them together and moving them like this. Just like we saw in the solution of this. Do you see it here? They are doing this, right? So it's this plus this. Sorry, it shouldn't go. So this plus this is equal to this. Okay? We will talk more about this next time. Thank you very much.